Hi.
Session, I have shared the materials also. Have you practiced all the specification? I shared the specification also.
Yeah, I have gone through that PPT presentation document, and through the specification, I didn't went all the chapters, but until
Okay,
chapter 3, I have been done. Chapter 4 is only one operating state that is already present in my PPT.
okay. Let me see what. By Apb protocol, write transfers, strobe, read transfers, error response, protect signal, awakening, and rules the parity check it and these. Okay. Mostly whatever we discussed, everything will be covered here. Okay. First of all, in chapter 1, it's very simple, like what is meant by Apb protocol and what are the applications of APB protocol. What is the difference between AXI and APB? Okay. Next to chapter 2, signals. We already discussed all these signals. Clock, resetter, addresser, protector, selector, enable, write data, strobe, ready signal, period data, slave error. Wake up. Wake up user, A user, W user, and PR user, PB user. Um, Wake up signal indicates any activity associated with an APB interface, and user is recommended to have a maximum with 128 user signaling. Here detailedly given all the signals signaling, but mostly we don't use these signals. Okay, maybe in industry,
Okay.
if any requirement is there, based on the requirement, we use the signals, wake up signal and user signal. Okay, till error response, protect unit, read transfers, write strobes, write transfers are completed. Just understand the theory of uh, this wake up signal. In which case we can use, so what is the difference between P wake up signal? So it is recommended to wake up be asserted at least one cycle before assertion of P select to prevent the acceptance of new transaction being delayed. Okay. So it is recommended to be deasserted when no further transfers are required. Okay, whenever new transactions we are getting like multiple number of transactions at a time, from one transaction to another transaction, we need to use this wake up signal. Okay. So next to user signaling, PA user, PW user, PR user. Just read this theory part. Okay, and user signal recommendations. So in which case we can use like that detailed specification and operating states. Anyway, we have discussed the operating states and state diagram also detailedly, and interface parity protection. Here protection using parity detailedly given, but whatever the protection is there, privilege access, data access, instruction access, and non-privileged access, that thing is important. Okay, and parity check signal, these are just understanding. Okay, that's why I shared the specification. If you want to understand detailedly, just have a look, take some time. Just if you spend 1 hour time, you can complete entire specification, just 46 pages. But if you go to AXI or AHB, it will be nearly 150 to 100 pages will be there. But still, we need to read at least one time. Entire specification, try to read at least one time. Okay. So today we will discuss on how to create the system Verilog test bench. Okay, I will give you the UVM test bench also. If you already know UVM, you can work on UVM test bench. I and system Verilog, everyone know, right? And also we will try to work out on like how to write the test plan, how can we write, and how can we write different type of test cases. I will just explain. You can try from yourself. Okay. System Verilog, whole test bench architecture, we will discuss. Yeah, any doubts? Someone not talking?
Can I ask a question?
Yeah, tell.
So Amba, mostly we don't, just we walk through the design code. That's it, right? Or we will develop that design also from the scratch.
We will
Mostly.
develop a design from scratch and also system Verilog verification for APB and also AHB. AHB also we are developing from scratch entire design. For the design, we are going to write the UVM test bench for AHB. AXI, we are
And
developing UVC. UVC in the sense we don't have the actual RTL design. We will generate a master and slave both as
yes,
a test benches. Okay.
got it. Back to back transfers.
Mm. In AXI, we are going to design like two master, two slave, write master, write slave, read master, read slave.
Sure.
So two.
Okay.
So it is very complex, but I will try to explain now all. Okay. So you can take some time and you can revise. But as of now, we will complete the APB protocol. We are going to complete with the design and also test bench.
Thank you.
APB is very simple. You also can write if you know the final state mission how to write. You can develop.
Hmm.
I also have APB RAM SV test bench also. If you are interested, I can share. You can work on it. Next. So first of all,
Yes, sorry.
how to write the
Sorry to
design.
sorry
Yeah,
to interrupt again. Uh, on the tool, First Sim tool, are you taking any half an hour session based on your availability? How to set up all these things, or we need to do everything based on the video you have shared?
what Questa Sima? Okay, Questa
Yeah.
Sim. I will explain the process how to do. Okay. Have you installed?
Hello, hello,
Have you
Prashant.
installed that Questa Sim?
Yes, I have installed, but my system is Windows 7.
Okay.
Installation is done, but I need to look to that video and I need to fix it again. I think something is
So
missing.
are you able to open the Questa Sim and also GVM editor?
GVM editor is good, ma'am. It is able to open, but when I
Okay.
open this FASTA, right, it is asking me to point out the exact FASTA sim, some library access, some file is missing. I think I downloaded everything properly, but I will cross check it again. Okay, through once I will go through the video,
Okay.
then
Okay. Fine. Fine.
Hello,
Everyone try to
Prashant.
install the Questa Sim. Whatever I have shared the video, actually it is explaining very clearly. Even if I explain now, again it takes lot of process, right? It will be confused even for you. That's why I have shared that video. If you don't
okay,
get, let me know. In weekdays, we will schedule one session
Yeah,
for
hello. Hello,
Questa
madam.
Sim
Actually,
installation.
this processing software, okay, you will provide us
Yes, I have shared the links to download Questa Sim.
okay, in this group.
Maybe you are not there. I will share the
Yes.
links again so you can download.
Yes.
Okay, and then the installation process also I have shared. Everyone once install, I will tell you uh, how to do the simulation, how to do the verification because GVim we need to integrate here. If you want to use directly QuestaSim, you can use here. There will be a jump start and create a project you can create and also suppose create new file. Here you can select system verilog. Okay, system verilog is available. So from here you can select and you can run the test. You can write the program, you can create one design file and also one verification test bench file, and then you can run directly. But if you want to integrate with a GVim, we need to use the commands. Okay, so once everyone install properly, I will tell you how to use the QuestaSim. Okay, so try to install by Wednesday. Okay, so on Thursday session we will discuss the how to use the QuestaSim. Okay. Any other doubts?
No, we can continue, Prashant.
Okay, fine. So how, first of all, design program, APB RTL design. For UART and I2C, how we have designed for UART, we took a transmitter block and a receiver block and generated the baud rate, and top level we have connected the transmitter, receiver and the baud rate. Same for I2C protocol, we have generated the finest state mission with a different number of states and design and also verified using system verilog, right? In the same way, APB protocol also we have default FSM, small FSM is there with the 3 states. Okay, so by using that FSM, we can generate the code, FSM code. Okay, so whatever wait state, without wait state, um, maximum in this design, we have P protect signal, not P protect. It's a very complex design, but it is not required. We can take simple design. Okay, first let me explain the FSM. So APB slave.b5 module slave. Slave is a design, master will be the test bench. Okay, so module APB slave. What are the inputs and outputs? Clock, resetter, P address, P selector, P write data, P read data, P write, and P enable, P ready signal. So these all are input and output signals. So declaring all the signals here, and also output range, P ready signal, output, P read data. Next, range 1 down to 0, present state, next state. Whenever we use the final state mission, we need to write the present state and next state. And also creating the memory here. And how many states we have? Ideal, setup, access, and access wait also. Okay, so ideal means 0 0, setup means 0 1, access means 1 0, access wait means 1 1. Like that, by default we can use the parameter. So what is the use of parameter? Just to assign the constant value. So whenever the value requirement is there, we can directly write the string name here. Okay, so next, write the reset logic here, always at the rate of passage clock, negate, reset, begin. If reset is high, it's active low. Active low means whenever reset is equal to 0, then you go to the reset state. That means present state is equal to ideal. else present state equal to next state. Okay. This is common logic for all. Next, always at the rate of star begin case present state. Based on the present state, the output is changing and also next state. Okay. Suppose present state is ideal. Then what is the next state? If P select is high, then next state will be the setup state, or else next state will be the ideal state. Okay. And we are in present state, setup state. The next state will be the access state. And current state is access state. The next state is if P ready signal is high, then if select is equal to 0, next state will be the ideal state. If select is 0, that means we are not selecting any slave here. Else, next state will be the setup state. Okay, P ready is high. If P ready is 0, we need to wait until the slave is ready to accept the data. If P ready equal to 0 means what? The slave is in wait state. That means it is in busy state. We need to wait until it get the signal as a high. Okay. So else next state is equal to access wait state. Okay, whenever P ready signal is 0, we need to wait until it comes 1. So it is a wait, access wait state. Next, current state is access wait state. Then if P ready is high, next state will be the access state. Okay, so in the access state, we'll do the actual operation. But if P ready is a low, it will be in a access wait state only. Still, we need to wait until P ready is high. That is what access wait state. Okay. By default, next state is equal to ideal state. Okay. So in this FSM, we written only what is the present state, what is the next state, but we didn't define what is the actual output. Okay. So for that, we need to take another always block. So always at the rate of POSH block, negate reset, begin. If reset is an active low, if reset equal to 0, P read data is equal to 0, else begin. If present state is equal to access state. In access state only, we do the write and read operation, right? Whenever P select is high and P enable is high. Okay. So P enable also. Okay. So whenever present state is equal to access state, if P write is high, then write operation. If P write is low, then read operation, right? So if P write is high, begin memo of P address is equal to P write data. So how we write the data into the memory? Select the name of the memory and to the particular address, we need to pass the data. So memo of P address is equal to P write data and P read data is equal to memo of P address. Read data means whatever the data is there in memory location, that data will be assigned to P read data. Okay. Clear till here?
Hello, Prashanti, one more. This is present shift logic can explain once. Present state logic. Present state logic can explain once.
Present state logic. Okay. Where here?
Present. Oh, yes. How this present state will get access to it?
How present state will get the access state here?
Yes.
Huh?
Yes, that is
Line.
next state.
In which line I am asking?
Actually, that is present state. Sorry, next state should be assigned to present
Present
state.
state will be the left hand side is a present state. Suppose ideal is a present state. Ideal present state means what will be the next state setup. Okay, but we need to write the condition. If if any slave select is high, then only it will go to the setup state, because in setup phase p select is equal to 1, right? In the access phase, p select must be 1, p enable must be 1. Then only we can do either write operation and read operation. At parallelly, we need to check the protect signal, not protect, p ready signal also. Okay, so that's why in ideal case we are checking whether p select is high or not. If p select is high, next state will be the setup state, or else it will be in the same state only. Suppose now we are in present setup phase. Setup phase means automatically next phase will be the access phase. Okay,
Like
suppose
my
we
doubt
are
is,
in access phase. Tell what?
actually this present state should be, if there should be some assignment to the present state. Right?
Here,
Yes.
okay.
Like present
You are
state should be like
okay. You are telling like present state is equal to something, next state equal to something
yes,
like
yes.
that.
Yes, present state should be some
But here
non-blocking.
we are writing case as a present state, right? Present state we are defining here. Present state in case we kept so automatically we are writing here present state setup ideal access left hand side.
But it should be assigned based something to the present state. But assignment is not present.
Okay, so
If
what
present state
you
assignment is good, then the case will execute okay, whether it is ideal setup
your
or not.
voice is very low. Can you speak loudly?
Actually, the present state has to should be assigned something. Some assigned
Okay.
state and working next state. Then only that case will execute. Right?
You are telling to the output
Not output this
in the present
that
state.
present state.
Uh,
I think that is parameter, right? That is parameter there in present state.
mm, okay.
It has to be assigned something
Um,
like some assigned present state, some non-blocking state.
it should assign something to the present state. Okay. Can you write a small piece of code like what you are thinking so that I can explain?
Okay. Sure.
Huh? Just write in the chat box.
I am writing.
Okay. What? Speak loudly.
I have written that the present state assignment is not there.
Okay. Present state. Assign present state equal to next. Okay. We need to write that. Here we have written right. Present state equal to next state. Whenever reset is not high, present state equal to next state.
Okay. So that I understand. This is what like I am looking.
Is it clear?
It's clear.
Okay. Okay, so this is what we are just defining what are the next states, and then so here if p write is high, then doing the write operation. You already know how to do the write operation and read operation, right? Same thing, however, we did for memory for writing the data. We just select memory of address is equal to write data. For reading the data, nothing but retrieving the data from the memory. So mem of address data will be assigned to the p read data. Okay, so this is what pure data is equal to mem of p address and initial begin p ready is equal to 1 initially, and we are just force and release, just we are using directly when should be ready is equal to 0 and when should be ready is forcibly to 0 and release. Okay, so this is what design for APB protocol, simple design. If you want to write in your own style, if you want to write in a more complex design, you can try. We already have another type of design also. This is another design. Here also same, inputs, outputs are declared, memory is created. Here through enum data type created the these setup write read. Okay, so states setup phase write read, and then always at the rate of posage clock and reset. If reset is high, p ready equal to 1 memory, and case state setup phase. In setup phase we have written okay, here didn't took the ideal phase, directly came to the setup phase. So if p select is high and p enable is a 0, and then if write is high, then go to the write state, else read state. Okay, so here didn't took the access phase, instead of access phase directly write and read phase. Okay, so suppose current state is write, then what is the condition? P write should be high, p select should be high, and p enable should be high. So then only we can do the write operation. So write method, and then read operation same. Read for read else condition we have written here. Okay, fine. So state is equal to setup read phase. Or else if you want to write like this, p write is 0, so not p write, and p select p enable must be high. Like that also you can write. And if you see write task, here it is a write task, whatever the write task we are calling here, it's a write task. Case p address modulo 4, it is generating a modulo 4 value. And if it is a 0, p address is equal to p write data 7 down to 0, and address plus 1 plus 2 plus 3, like this entire 32-bit data assigning in this way. Okay, because p address is up to 4, right? 0 1 2 1 2 3. So next here also, and for second case, and then third case 0 1 2 3. By default just default statement, and for read also same. For read operation, p read data is equal to mem of p address data assigning to the read data. Separately we have written. Okay, so this is somewhat complex, but instead of writing like this, you can write in a simple code here. Okay, any doubts still here?
So in this simple code,
Ma'am, can you please again summarize?
P enable, where do we consider
Wait.
as not?
Tell what?
Yes, ma'am. In FSM, no, where we already considered P select line and P ready, but P enable line we not considering. Like P enable also should be one when we are taking the data.
Here, okay, we can write the p enable also. Here didn't took the p enable. Okay. Then here whenever p ready is high in access phase, how you can write, or else here present state is equal to access phase, then write operation. If present state is equal to read, then read phase. Okay, so here in access phase itself we can mention whenever p ready is high, and write p select equal to 1, enable is equal to 1, like that you can mention here in the access phase. I think in the one example I have mentioned like that.
Yes, ma'am. In the means after that one EVM code, so there enable also mentioned. So here it not mentioned. Okay, we can mention that.
Apb master. Okay, this is Apb slave right access phase. See here. Setup phase. In setup phase, p select is high, enable is not high, and when p write is equal to 1, then it go to write access state, and whenever p write is equal to 0, read access state. Okay. Now in write access state, p select is high, p enable is high, and p write is high. Then we can do the write operation. Okay. So if valid signal is equal to 0, p slave error equal to 1, else p slave error equal to 0. Like that, read. Read means p select must high, p enable must be high, and p write must be low. So we can read the data. And slave error also checking here. If valid, if the data is valid means what? Correct. Correct means it is a 0. Equal to 0 means p slave error is getting 1. There is no error. Else p slave error is equal to 0. Okay. So there are different examples. We can try any example. Okay. These all are multiple slaves. Yesterday we have seen where we connect with one memory, one master to the multiple slaves, right? A slave 1, slave 2, slave 3. So here we have created a number of slaves. Actual Apb slave is this one. By using this actual Apb slave, we are creating the 3 number of slaves. So here ready signal, slave error signal. Okay, see here slave 0. This is slave 0, slave 1, slave 2, slave 3. 3 number of slaves. So master will access any one of the slave. I will explain this code. Master side input reset ready p slave error FIFO full. Okay, through the FIFO just connecting the master and slave. Actually FIFO is a communicator between the master and slave. So here actual phases. So ideal phase, setup phase, access phase, like that. By using FIFO, connected the Apb master to the slave, and one slave as created, and slave block. Okay, this is main Apb slave RTL connections, top level. In slave sections, we took the slave 0, slave 1, slave 3, multiple slaves. I will share this code. Everyone work on the code and try to understand. Okay. Actual design. Okay, main design program. If you want one master to multiple slaves, this design will be good. Okay. Our main concentration is a system verilog test bench, right? So we will go with this design example. Okay, is it clear?
Yeah. So the design which you are currently using for the test bench, which don't having please slave error, all these scenarios, right? It's like a
Yes.
we will do the basic
Yes.
read write transfers with weight and without weight.
Yes.
Okay, thank you.
This is for
So the
system
other, yeah,
verification. So if you
got
want
it.
to concentrate on system verilog, this, but if you want to concentrate only on design part, I can share this.
No. I'm just asking.
Mm.
Oh, fine, you can continue.
Ma'am, can you share three of them, like first the design part, then the SV and UVM, so we can work on three of them?
Yeah, I will share. I will share all three. Okay. First, work on the design. This is try to understand all these blocks, how the interconnection, and try to draw the block diagram. Suppose if you see here, FIFO, including the APB master, and APB master have including slave section, and APB slave included with some and top level design, having all these four blocks. Try to understand how all these four blocks are interconnected. Okay, so that you will get full-fledged APB design. Okay, so we'll look into the system verilog test bench. So this is what simple design for by taking the present states and next states and write read data. Okay, so first of all, whenever we are writing a system verilog test bench, we need to start with the interface block, right? So first of all, create the interface name, and what are the clock reset signals we need to pass within the interface. Okay. Next, P address, P write data, P write, P selector, P enable. All these are inputs declared with the logic, and even outputs also we need to declare with the logic, right? So without using reg or while, we just use this data type. And clocking block. Uh, Here I already told, for driver, inputs will be working as a outputs will work as a inputs. Okay, so clocking block, driver, name of the clocking block at the rate of POSH clock, default skew. What is the default skew? Input #1, output #1. It's same like a time scale. We write the time scale, right? In the same way, these inputs will be uh, working like a sample the data. #1 means we don't get a much difference. If you take #5 like that, actual input delay will be added with this sampling data, sampling time. Okay. So outputs are declared with the P address, write data, P write, P select, and P enable. Input, P read data, P ready, and clocking. And monitor. This is what for driver, and monitor clocking, monitor CP at the rate of POSH clock. By default, this is skew, and declaring all the inputs, because for monitor, the data is getting from the DUT, right? From DUT to monitor. That means all signals will be inputs to the monitor, whether it's output or input. And clocking. um, Next, mode port. Mode port is just for declaring the port list. So for synchronization purpose, we use the port list. For one is for driver, one is for monitor. Okay, so this is what the interface. After interface, next thing is transaction. We need to write the transaction class. So transaction class, in that we need to mention all the inputs and outputs. Inputs must be declared with a rand data type, rand or else rand C. What is the difference between rand and rand C? Rand means all the values will be generated, even multiple number of times it will be generated. But rand C means it doesn't generate the multiple repeated values until one cycle is completed. So that's the difference. So declaring the input and output values here. Next, constraint, writing two constraints, constraint C1 and constraint C2. So P address must be generated 10 to 20 only inside constraint. Okay, so you can use any type of constraint, inside or soft constraint or inline constraint, whatever. So here P address inside 10 down to 20, so it will be generated the value in that range, and P write data inside 50 down to 100. Write data will be 50 down to 100. Function void display. So just displaying the data here, passing the string name, class name here, and by using the dollar sign, just a line, and dollar display printing the values. Write data, address, P write signal, and read data signal. Okay. So this is what the transaction class. Whatever the data we have written in the transaction, we need to do the randomization through the object. So we can access all these data through the object, transaction object, right? So just go to the generator block, class generator, rand transaction tr, mailbox gen2 drive, and creating the function new mailbox. Okay, so this dot, nothing but creating the nothing but creating the memory for the class with the respective connections, because for generator block we have only one connection, that is mailbox, but for driver we have two connections. One is a mailbox connection, one is a interface connection, right? So that's why we need to pass two arguments, but here one connection is enough, that to mailbox. Okay, so within the class we are accessing the same data, right? That's why this dot gen2 drive, this mailbox name is gen2 drive, so this dot gen2 drive equal to gen2 drive end function. Okay, next task, main task, repeat of 10 times, that means randomizing 10 number of times. Okay, repeat of 10. Tr equal to new, tr equal to new means already here we created the transaction tr. Okay, so tr equal to new means assigning the memory to the object. Without assigning the memory to the object, we cannot, it doesn't store the data, right? Even it do the randomization, but still we get the output as a 0 because it doesn't store the data. So create the object here, and through the object only we can do the randomize. So tr.randomize means what? It directly go to the transaction class. So whatever the data is there, input data which are declared with a rand, all the data will be randomized here. tr.randomize, and gen2 drive dot put of tr. Okay, gen2 drive. That means what? Whatever the data is randomized in tr, we are putting into the mailbox by using put method. Okay, can you tell me what is the difference between put method and get method?
Put method is used to insert the data into the mailbox. Get data is used to retrieve the data from the mailbox.
Okay. Any other
Both
answer?
like blocking, both are like a blocking method. So until you randomize and complete, that object is randomized, until it will wait to receive the data and it will store inside that mailbox. So there are two ways, blocking and non-blocking handle. So
Okay.
this is predefined methods for the accessing the data and retrieving the data through the mailbox.
Okay. Okay. So that's what the difference between blocking and non-blocking, which is waiting for the transaction, which doesn't wait for the transaction by using try put, try get. Mostly we don't use try put to try get because they don't wait, right? But put method means it will wait. If even transaction is not available, it just wait for some time. Okay, so that's why mostly we use put and get method. And next tr.display, calling the display method from the transaction class, whatever function we have used here, we are calling that, and dollar display gen2 drive. Okay, next after generator class, we need to start with the driver. So driver means what? sending the data from generator to the DUT. So first it need to get the data from the generator via mailbox. Okay, and then it need to send to the DUT via virtual interface. Why? Because normal interface we cannot use the physical interface. It is static in nature. So for that purpose, we are using the virtual interface. How we can create the virtual interface? Suppose if you see here, class driver, name of the class is driver, creating the virtual interface with the name of the normal interface. Apb int f is the name of the interface here. With that name, we are creating the virtual. Apb vif is the name of the virtual interface. Now, whatever the data you are accessing in the DUT, whatever the signal, you need to access through this Apb vif only, not through Apb int f. Okay. Yeah, tell what's your doubt.
Yeah, ma'am, what is meant by line number 1? Like define, you defined, right? So what is that connection meaning?
Which
Driver
one?
interface, line number 1, defined.
I will explain. Okay, so here we need to declare the virtual interface. Okay, next mailbox declaration and transaction class. Okay, next creating the function new constructor. Okay, next reset task. First one is a reset. Even in Verilog HDL we write the reset, right? So how we write the reset? Just initially reset equal to high, and after 10 time units or 5 time units reset equal to 1, like that we need to do. In the same way here also we are writing as a task based. You already know what is the difference between task and function, right? Mostly system Verilog test benches we use everywhere these task and functions only. Okay, so task reset, wait until a reset is active 0. This reset is active 0 here. So whenever reset is equal to 0, then only the output will go to reset state. Whenever reset is equal to 1, the output will be in a functionality stage, like it do its own, whatever the functionality. Okay, so dollar display reset started. Next, if you see here, drivif dot p write equal to 0, select equal to 0, address equal to 0, write data equal to 0, write enable equal to 0. All signals are going to 0 because reset is high. Okay, in the same way here write task. So here we written 28 line gen2 drive dot get. That means what? Whatever the data is there available in the mailbox, gen2 drive mailbox, that data we are getting here by using get method. In the generator, by using the put method, we just kept in the mailbox, right? In the same way, by using the get method, we are getting the data into the driver. Okay, and calling the write task. Write task is available here. Okay, what we have written in the write task? We are writing the data to the signals. How you can write the data to the signals?
Accessing through the interface.
So generator, driver, monitor, scoreboard, and here there is a interface and there is a DUT. Okay, now we got the random data which we kept in a transaction TR. So this TR data we are putting into the mailbox by using the put method. We kept into the mailbox temporarily, and driver getting the data here into the driver. What is the data? It's a transaction data, TR dot data. Okay, now this TR dot data we need to send to the DUT. How we can send to the DUT? Through the interface. But really, we don't use this physical interface. We create the virtual interface. Already we have created the virtual interface in driver, right? So now, whatever the signals available, suppose here address, data, and p strobe signal and p select signal, whatever. Okay, so these signals are not nothing but virtual interface, VIF signals. Okay, VIF dot address, VIF dot data, like that virtual interface data. So you need to write tr is equal to tr.address is equal to VIF data is equal to tr data. That means the transaction data you are sending to the DUT via virtual interface. Okay. So these variables are there in a interface, but you need to access through the virtual interface. Okay. So that is why we written here DRIVF. Actually, in this place, you need to write this connection, this path. What is this path here? Apb VIF is the name of the virtual interface. Dot driver. What is this driver? Whatever we written in an interface, the driver is nothing but mod port name of the interface, because these signals you are accessing. How you can access these signals which are available in interface? We can access through the virtual interface. Okay, so that's why we connected that path there. So driver dot clocking block driver CV. Okay, that is how you can access these internal variables. So that's why we set the path here, apb dot driver cb. Okay, so is equal to so top level we just kept like this. The name of this macro is drivf. Okay, so that's why whenever you are accessing that path, we mentioning drivf path. Instead of this drivf, you can directly put this whole path every time. Okay, so every time you need to put that path dot pselect dot enable dot write dot address dot write data, like that you need to mention whole path here. Okay, so to this interface data, we are passing the transaction data. So right side will be the transaction data, left side will be the interface data. That is what write task. Read task also same. But for read data, left hand side will be the TR data and right hand side will be the interface data. So this is what the driver, okay, getting the data from the mailbox and sending to the DUT. Clear everyone? Driver logic.
Can you please explain the write method once again?
Write method. Okay.
Write task, sorry.
So here select drivf dot select. Suppose instead of that I am putting this whole path example. So where we have this select signal in this path, apb vif dot driver cb dot select. Here we have that select signal. So we are accessing through the virtual interface dot mod port dot clocking block. Okay, in the same way, here also I am removing p enable, and here every time you need to use this entire path. Okay, so without using this complex code, just at the top level globally, we are using this path here by keeping a macro. Okay, so this is how we access the data, and the right hand side will be the transaction data passing to the VIF data. Okay.
Yes, ma'am. Yeah.
So driver means transaction data sending to the virtual interface. Now monitor. Monitor is also same as a driver, but just reverse operation, because virtual interface data is sending to the TR data here. Right hand side will be the virtual interface, left hand side will be the TR. Okay, so TR is equal to VIF. Okay, so monitor will get all the data. Now this transaction data is sending to the scoreboard via mailbox. In the scoreboard, we write the output, whatever to print in the log file. We write the display statement, and also we do the comparison. Comparison logic also you can write, because in scoreboard mostly we write the checkers, right? Last time I have shown you some example in I2C protocol how we write the checker. So same way we can write. Okay, so coming to the right monitor. For monitor also same, we define the path here, but which path. Before we have took this driver path, now we need to connect with the monitor path, because whatever the signals are there in the monitor clocking block, we are accessing those signals. So that's why virtual interface dot monitor modport monitor dot clocking blocks monitor cp. Okay, that is what the default path. So we need to set that class monitor virtual interface we need to declare, and we need to create the mailbox and class constructor. And in the main task, if you see here right hand side all are virtual interface data which are connected through this macro, and left hand side will be the TR data. Now we got the TR data. Okay, this TR data we need to send to the scoreboard. How we can send to the scoreboard? Via mailbox. So if you see here 36th line. So in the 36th line we are putting into the mailbox. So whatever we kept in the mailbox, we get the data in the scoreboard. So here is the scoreboard. We created the class constructor, and also in 15th line, monitor to scoreboard get of TR data we are getting here, and printing the scoreboard. Here comparison logic I didn't written for Apb protocol. We'll see whether it is available in this UVM. Okay, here comparison logic is available, so you can check write operation, read operation. If what happens if it is correct, means invalid mode, or if it is correct, not correct. So it is printing here matched or mismatched. Once check this logic, okay, you will understand in UVM program we have the comparison logic. Okay, so this is what scoreboard. Everyone clear till here?
So Prashanti, we are not using any reference model. Like if you want to use reference model, like is there any suggestion? Like we need to mimic that design, right?
Here, here in scoreboard, what are the signals we have? Design signals. I will tell you how to write simple. Whenever P write data is equal to P read data, then our output is correct. Test passed. Okay. If P write data is not equal to P read data, test failed. You can write these two conditions.
That I getting, but in the system Verilog we have one more concept called reference model components, like so.
Reference model which we write in the scoreboard, or else we can write in the transaction class checker.
Okay, fine.
So for that, we need to
We
define
have
a
written the
function here.
checker.
Yeah. Like that, we need to
Same
define their
like that,
function here.
yes. You can write in a transaction or in scoreboard, wherever.
Okay, good.
So next to top level, this 4 we are connecting in a environment. So in environment, we need to create the generator driver monitor scoreboard, and creating the mailboxes and creating the virtual interface. So just call here, just call the task and preset pretest test and main test. So just call individually all the tasks. I think you know how to do this. So
Ma'am,
whatever
please
is
show the pretest function where it is written and explain it, please.
which one?
Pretest.
Test.
Pretest.
Pre-test.
That method is in environment only. Ma'am, he is asking about task pretest. Can you go a little bit down?
Here.
What?
Okay.
Yeah.
Okay, wait, I will explain. Okay, see here. Class environment. So before, however, we set the path here, however, we are accessing the DUT variables by using this path. In the same way, if you go to the system Verilog test bench architecture, have you remembered system Verilog test bench architecture?
Yes.
Where we have generator, driver, monitor, scoreboard. These 4 sub blocks we need to call in the top level environment. Okay, so how we call these 4 in the top level environment? In the environment, we create the instance for generator, driver, monitor, scoreboard. Before, however, the transaction data we have created in the generator, right? TR in the driver, monitor, scoreboard also everywhere we have created the TR. By using the TR only, we can able to access this transaction class and able to access all the variables. In the same way, in the environment, if you want to access this generator, driver, monitor, scoreboard, we need to create the instance, nothing but object. Okay, then only whatever presented here, preset task or main task or whatever the function, everything we can access in the environment. Okay, so that's why here we created generator, GEN, driver, DRIV, monitor, MON. Okay, and also created the mailboxes and also virtual interface. Okay, and also constructor, class constructor we need to create, right? So if you see here, in class constructor we need to create this generator, driver, monitor also. I already told you, for generator there will be one connection, that is what mailbox. So gen is equal to new of gen to drive. So whatever the function we have created here, new function, new mailbox. So we need to pass this argument, right? Here we need to pass the argument. So how we can pass the argument here? Through the environment. In the environment we will access like that. Here 9th line, there is a main task. So if you want to run this task, first of all we need to call this task, right? Without calling this task, it doesn't execute directly. So how we can call this task? In the top level environment, because generator is sitting in the environment, we need to run in the top level environment. So this main task we are running in the top level environment, like that. Driver, in driver also we have this function new. 2 connections are there, virtual interface connection and mailbox connection. 2 connections are there. Okay, and also here we have reset task. Okay, drive task. So these reset task, drive task we will call in the top level environment. If you see internal this task, internal this drive task, we have write method. So this write method we are calling from this task. This task we are writing separately internally in driver. If it is in driver, within driver we can call, but driver is sitting in the environment. So in the environment we need to call, because environment is the top level. Okay, so that's why here we have created generator, driver, instances and passing the arguments. Okay, for generator 1 argument, driver 2 arguments, monitor also 2 arguments, scoreboard 1 argument. Okay, now here in the environment we are creating a pre-test task. Okay, pre-test, test, post-test, like that we will divide. In UVM also we have callback methods like body, pre-body, post-body, like that. Okay, so in the pre-test we are doing the reset. Okay, whatever the driver reset task is, the driv.reset. So how you will access this reset task? Through the component, through this object, driver object. So we have created driv for this driver, right? The object. So that's through the driv.reset we are accessing this reset. We are calling this reset task in the environment so that it will run this reset task. Okay, in the pre-test. Now in the main test we are calling main task which is there in the generator, and also main task which is there in the here driver. Okay, and another main task which is there in the monitor. These 3 tasks we are calling from the top level environment. Okay, by using the fork join concept. It's a parallel communication, right? Parallelly, all threads will be executed. That's why fork join. Okay, that is what main test. Okay, in the main test, we are calling these three subtests. Next, task. We have pre-tested test. Okay, fine. Pre-tested test is there. Now, this pre-test and test we are running from the run task. Running from calling from the run task. So here pre-tested test or calling in the within the environment. Okay. Now we need to run this. We need to call this run task, right? So where we call this run task, we will call from the top level test.
It's top.
Because
Yeah.
top level test is the top level for environment. Okay, so then that run task we will call in the top level test. So here we have written test.sv. Within test.sv we will create the environment env, initial begin, created, and calling the run task env.run. Okay, now this test should be included in the top level test bench.sv. The test and interface both must be included in the top level test bench.sv. So go to the top level test bench.sv. Okay. Another thing is suppose here environment is there. Actually, in environment we need to include the all sub files. Hash include, tick include. We need to include all the sub files. This environment we need to include in the test. Test and interface need to include in the test bench.sv. That is what flow, exact flow. But without doing that, we have created one header file, header.svh here. In that header file, we have included all the files here in one place. You can do like this also, or else here also header.sp created. Okay. Or else you can include like this. You can create like this. Suppose if you see it's environment. Okay, so we will create a generator class individually, monitor class, driver, and scoreboard individually. In the environment, we will include all these sub files in the top level: transaction, generator, driver, monitor, scoreboard. Okay, and like that in test, we include the environment. In the test bench, we include the test and interface. Like this also you can declare, or you can create one header file like this. And by using that header file, you can. Okay, so test bench top level. This is what test bench top level. So Apb int f is a interface included here, and test included here, and written the dut here. Okay, so top level test bench and verilog file also written here. Okay, fine. So this is what system verilog test bench for Apb protocol. Okay.
Okay. Thanks.
Any other doubts, others?
Ma'am, please summarize once more.
Which one?
Ma'am, just give overview from beginning.
What?
And from transaction and interface from start, please explain again.
Okay. So whatever the system Verilog architecture, first of all, we need to create the interface block. Okay, so how we have created the interface block, we just create the interface Apb interf. We need to declare all the variables here and clocking block mod port. If you know the concept individually, first of all, you need to learn all system Verilog concepts individually. Okay, so then only you can apply these knowledge to the building a test bench architecture. Okay, so this is how we design the interface. And after interface, just create the transaction class. In the transaction class, what we need to include, whatever the constraints or whatever the input data you need to declare in the transaction, and the input data must be declared with the RAND data type. Why? Because that data we are going to randomize in the generator. The transaction data we are going to generate in the random, do the randomization in the generator to driver we need to pass. Already I have shown you how to create the transaction, declare all the input and output variables with a rand. If any constraints are there, write the constraints, and if display statement is needed, just write the display statement. Okay, so this TR data we need to create the object in the generator, because we are accessing the transaction data in the generator. That's why we need to create the TR here. Through this TR, you can do the randomization and put into the mailbox. Okay, in the driver, get the data from the mailbox and send to the DUT via virtual interface. This is how we can make the virtual interface. Okay. Next, monitor. Monitor also same, and scoreboard also same. And these 4 blocks we need to connect in the top level environment. We are calling the all tasks and functions in the top level environment. The top level environment will be connected in the top level test, and test and interface will be called in the top level test bench.sv. Okay, clear?
Yes. Ma'am, header, what is written in the header?
In the header, I just included all the files here before I shown you, right? Normally in environment, we include like this all subblocks in the environment, and environment will be included in the test and interface will be included in the top level test bench. So individual files you can include like this, or else you can put all files in here in the header.svh. This header.svh you need to include in the test bench top level here, test bench.sv. This is the default file in the EDA playground. So you need to mention this header.svh in this default file. Okay, so that remaining all will be running parallelly. Okay, clear everyone? Everyone try to install the tool properly. So if you install the tool, we can do some problems, some task in the QuestaSim. I will tell you how to run the QuestaSim.
Hello, madam. Hello. Actually, this EDA playground is open source website.
Yes.
Yes.
Hello.
It is open source. It is a open source. You need to verify it's your college account or company account. You need to validate your account actually.
If you have any college ID or company ID, you can use. If you use that, you will get the tools access with Cadence and Synopsys, the commercial tools access you will get, or else you can access free tool all deck.
Okay. Sure.
So see here, what is the output? Address, P address, randomizing 11, 17, 15, 14, 18, 17, 20, 14, 17, 12. Write data 60 is writing into the 11th, 90 is writing into the 17th, 80 is writing into the 15, 72 is writing into the 14, 97 is writing into the 18. Why? Because we took the constraints here.
Data should be inside that. Need to be randomized in between 10 to
Address is
20.
between 10 to 20. Write data is between 50 to 100. Okay. So that's why addresses, if you see, all addresses are randomizing between 10 to 20 only, and all data are randomizing between 50 to 100 only. Okay. So read data. Read side, what is the address here? Read is 0. Okay. Read is 0 means from here the read is started. So 1790, 1790, correct. 20 address. Read side it is generating 20 address, but the input side we didn't generated the 20 address. We didn't store any data in a 20 address. So that's why output is NAN. And next 17 address 19, correct. 14 address 72. 14 address 72, correct. Okay. So like that you can try different examples. Okay, we have RTL design and also UVM verification code. Just work on that. Okay, and if you want to write more test cases, how we write the test cases, different types of test cases, any idea?
By extending the existing test by using constraints. Through the inline constraints, we can do that. Or
Okay.
directed scenarios we can generate, or we can generate only randomized scenarios.
So what will be the test cases available for APB?
First, we need to do basic write. After, we need to do read. Then we need to check write reads. And these are the directed. So we can do random read write combination. One read after write, or like this. And we can conclude this with design supports. We can do wait, verify wait scenarios and no wait scenario that you explained in the session, right? If there is no wait, the one we verified is there is no waiting. So it's like there is no, we are not waiting for any ready to be high or anything. We are making that P ready as one from the starting of after reset. So because it's one slave, right? I have one question. If I want to add one more slave, like APB slave test, now I want to dual port ram dot s dot v I want to add. Okay. So so instantiation only will change, right? But so I need to write
APB
system.
separately, RAM separately, both you need to connect in the top level, whatever design.sv. So
You have, okay. You told you will share that one master multi slave. I can go through
share.
that if you give the access to us. And
Okay, sure. Okay, so everyone try like how many test cases you can write. Some more test cases is nothing but different scenarios, like what different scenarios you can cover. Okay, and try to write some coverage report for this. How we write the coverage? Just create one coverage model. Whatever the bins, write the bins for p address, p write data. Okay, so check whether how many bins are covering or not. Okay, so just try to generate small coverage report. If you want, I will share the reference also for coverage.
okay.
So this is UVM example for coverage report in assertion, in adder. So this is how you can generate the coverage, simple coverage. I will share this code. Okay, try to write and check for this example, Apb example. Okay.
Ma'am, please share the whole design because what is in transaction class we don't know. If you send the whole, we can apply.
Okay, fine. Okay, fine. So that's what for today's session. In the next week,
Ma'am,
we will discuss
what is
on
right under the 2.p files? Please show again.
.v file. Where here,
No, no. Yes, yes, yes.
here.
This two, this two.
This
APP
is
slab, APP
this
slab
one.
test.
This is normal Verilog test bench. This one we didn't included anywhere. It doesn't generate slave dot. We didn't include it anywhere. Just avoid that. Just simple test bench because whenever you're designing some system Verilog test bench, okay, whatever the design you took for practice, okay, first of all verify it in a Verilog test bench. If the design is working fine in the Verilog test bench, then only start working with the system Verilog test bench. Okay, so that's why here I have written same Verilog test bench first for the same design. So it is working clearly, perfectly, then started with the system Verilog test bench. Okay, so you also, whenever you are trying to design something in SV, first design using system Verilog. Once you get the output, then you can move to the system Verilog. Okay.
Okay. Ma'am, you in last class you told that you will told the how to write test plan. Please explain that.
See, test plan in the sense that's what I told now. Just take one sheet, just take one Excel sheet or whatever. You can even take your blank, whatever your book also. Write all the signals. Suppose in APB signals, APB protocol, whatever the signals are there. So what signals we have? P clock, P reset, P address, P write data, P read data, P write, P select, P enable, P ready, P slave error, P protect, P that's it. Okay, so just write all the signal list here. And coming to the test cases, suppose first of all you need to verify one test like reset test, that is one test. Second, you need to verify the write transfer, so that will be the second test. And next you need to do the read transfer, that will be the third test. And next you need to do the whether it is a wait state or not. So P ready is asserted or de-asserted. You want to check the wait state. So that is one test. Okay. Nothing but checking all the features. Okay. So any other features are there in here slave error. Slave error you can check. That is one feature. Okay. So like this, write all the features, whatever the possible scenarios you want to verify. So reset means what we need to write in the test bench. Write transfer means what need to write. Already we did these things in driver logic. So if you see here, read completed, write completed, reset completed, like that one by one. Test plan is nothing but whatever the design is there, how you are going to verify that particular design. What are the corner case scenarios you need to verify? What are the all features we need to verify? How to verify? Just taking one plan, just like creating one sheet where you will get all the information. Based on that, we need to proceed. That's what test plan. Okay. Clear? Any doubts?
Yeah.
Okay. So in the next session, we are going to discuss on AHP protocol. Okay. So take the time for this whole week and complete APB protocol perfectly.
Okay. So after
Ma'am,
APB, after AHB only, you will start with bridge, or the bridge will
Yes,
complete it in AHB only.
yes.
Ma'am, the sheet you sent
What?
yesterday, can you explain the sheet, the interview questions which are there? Just
Interview.
explain.
Uh, Whatever I shared yesterday, no?
Yes, yes. That PDF only. Just overview.
Okay, wait, let me see.
I don't have any questions. Can I leave, Prashant?
Okay.
Thank you.
ma'am, can you please share the yesterday and today session also of protocol?
Okay. So these are what I shared yesterday, right? What doubts you have here? Same whatever the code I explained here. UVM questions also used. If you know UVM, just go through that. If you don't know UVM, uh, just revise only system Verilog. And here differences APB, AHB, AXI. And here system Verilog assertions. You must know individual topic first of all. What is meant by coverage? What is meant by assertion? How to write? And then these all are assertions only. By default, if you have knowledge, then only you can do this. Okay. And what are the major challenges in APB interface? Like how the questions will be getting. These are all self-learning questions. What doubts you have? Tell me. I will explain those.
Ma'am, assertion.
Assertion. Assertion. How to write?
Yeah, I know, but just explain.
Assertion example. This is what first example. Okay, can you tell me what is the difference between immediate assertion and concurrent assertion?
Ma'am, immediate assertion occur in the same cycle. Concurrent is for multiple time. It will check multiple time.
Here, problem statement. What are the conditions for a successful APB transfer? A transfer, okay. And write a system verilog test bench, system verilog assertion for APB components. Okay. Assertion 1, P ready should be low in the setup phase. Okay, so property and property, whatever the assertion we need to write within the property and property. Name of the property at the rate of POSH clock, disable if preset is active low, and then P select is equal to high and P enable equal to 0. Then set assertion to the P ready equal to 0. Okay, if P ready is equal to 0, then assert property, here it is checking, else it will be getting the error. P ready is high in the setup phase. Okay, P ready is high in the setup phase. So it should get as a, if here you can write the condition like not P ready, or else directly you can write P select and not P enable is equal to triggering. Triggering to P ready is high. Directly you can write the error statement, or else you can follow like this. Just assertion P ready should be low in setup phase. That's what. If it is a high, we'll get the error. Here it is low only. So this assertion is correct. That's why here directly printing assert property. Okay. In the same way, P ready should high in the access phase if the transfer is successful. Access phase means P select should high, P enable should high. Then P ready equal to 1. If it is correct, then it's a correct valid, or else P ready error statement is printing here. Like that, if P write is high, P write data must be stable during the access phase. P write is high, then P write data should be stable during the access phase. Okay. P select and P enable, P write high. $P stable. Okay, $stable written. Okay, that means without changing. Whenever this condition is satisfied, without it should not change the value. Like that, these are different assertions. Just practice, try to understand each one. There are a lot of assertion examples. Okay.
Okay, ma'am.
Any other doubts? Others? These all are basic syntaxes only. Just you
Okay.
need to write this single line functionality. Remaining all are basic syntax.
Please send the EDA playground link.
Okay, fine.
Ma'am, last time you sent the drive file, it's unable to access.
Okay, fine. I will
Ma'am,
send drive link only, not directly EDA playground. If I send directly EDA playground, at least you are not doing some changes, at least few changes. Okay, if I send the drive link, at least then you will copy the same codes and you are trying in the tool. At least you will get to understand where you need to include the file top level. Okay, so that's why I share only drive link, not EDA.
okay. Ma'am, please send the both that you shown.
Okay, okay, fine. Then Venkatesh, Ashwini, and Ranjit, Akash, any doubts? Akash or Ashwini?
Yeah, no doubts.
Okay, okay, then thank you all. Bye.
Thank you. Please send ma'am as soon possible.
Okay.